So in the previous videos, we talked about internal energy transfer from system to surrounding. So system, surrounding. System and surroundings can exchange internal energy as heat or they can exchange energy as work or a combination of both, meaning it could be delta E is equal to Q plus W. Now, if a reaction is being carried out in constant volume, so constant volume condition. Constant volume. What does constant volume mean? Volume of the reaction does not change, meaning delta V will be 0. If delta V is 0, then this particular factor in work will become 0. So then work will be 0. So in such conditions, in a constant volume condition, work is always 0. Then what will happen is that delta E is completely only heat exchange and there is no work quantitative. There is no work quantitative. So at constant volume, change in internal energy is all via heat and no work. So you can use an instrument called calorimeter, and in this specific case we learn about bomb calorimeter in 1211. So what's a calorimeter? Calorimeter is a device in which we measure thermal energy exchange. This we measure thermal energy exchange. So this contains a sealed container. This instrument contains a sealed container in which sample is placed and we take it through the reaction. When the reaction takes place, there will be a change in temperature, and this change in temperature is related to heat absorbed by the entire assembly. Okay, heat absorbed by the calorimeter. So what happens? The heat absorbed by the calorimeter is equal to heat capacity of the calorimeter multiplied by change in temperature. Then, if we can measure the change in temperature using thermometer, we know the material with which the instrument is constructed. Okay, the entire calorimeter assembly, okay, is a heat capacity of the entire calorimeter assembly. We know the material with which it was made. We can measure the delta T using temperature. So that's how you can calculate the heat absorbed by the calorimeter. Now, what is heat absorbed by the calorimeter? Heat absorbed by the calorimeter is nothing but heat given out by the reaction. So whatever heat is given out by the reaction that is taking place inside is all absorbed by the calorimeter. Of course, this assumption is valid. This assumption is taken for granted. We are assuming that all the heat that is given out by the reaction is absorbed by the calorimeter and nothing escapes. There is no loss of heat. So if we can read the change in temperature, if we know the material with which the calorimeter was made, so we know the heat capacity, we can calculate the heat absorbed by the calorimeter, and then that will be equal to the heat given out by the reaction. Now, if there was a sample of 1.010 grams of glucose and we take it through a combustion reaction, and we know combustion is heating up in oxygen, and we get water and carbon dioxide. Let's say 1.010 grams of glucose was combusted, okay, in a calorimeter, and it resulted in a rise of temperature from 24.92 Celsius to 28.33 degrees Celsius. So again, 1.010 grams of glucose was taken through combustion in a calorimeter, and it resulted in a temperature change from 24.92 to 28.33 Celsius. What is the delta E of the reaction? This is our example, problem example. Now, heat capacity of the bomb calorimeter is 4.90 kilojoules per Celsius, and this is information given to you, okay? So then what is the change in temperature? Delta T, right? Which you can measure, you can calculate from here, okay? So delta E of the reaction, okay, delta E of the reaction, and we want to get delta E for the in this case the reaction is combustion, so we want to get the delta E of the reaction of combustion of sucrose in kilojoules per mole of sucrose. We need this to be the units, kilojoules per mole of sucrose. So then delta E of the reaction is equal to, let's get the change in temperature first. Change in temperature is 28.33 minus 24.92, which is 3.41 Celsius. We know formula for Q of calorimeter, which is heat capacity of the calorimeter multiplied by delta T. So this would be 4.90 kilojoules per Celsius, and I'm going to keep the units going here because we want to finally end up with this unit specifically, multiplied by 3.41 Celsius, and when you do that, you will get this answer as 16.7 kilojoules. So that means heat of the reaction is negative 16.7 kilojoules, okay, but we want to get it in kilojoules per mole. So what do? We say negative 16.7 kilojoules. We know we have used up 1.010 grams of sucrose, but we know that every 1 mole of sucrose is 342.3 grams of sucrose, and this value we obtained from periodic table. By calculating the periodic table, we obtained the values for carbon, hydrogen and oxygen, and we calculated the molar mass. So then grams will get cancelled, and this will turn out to be negative 5.66 times 10 raised to 3 kilojoules per mole of sucrose. So this is another kind of quantitative example of one of the types of questions. It's another kind of quantitative type of questions that you might come across in this chapter.